Okay. 1, 2, 3. Am I live? Check, check. Sound check. Video, audio, how everything is going. Hopefully everything is okay. And we are live. Alright. No noise. The sound is good. Last time I had some noise issues due to the USB charger. Hopefully this time everything is better. Alright. So today I wanted to show some things I did last week and also show some updates on our home lab. So right now I actually have 2 calibrators running over there and spend quite a lot of time to adjust them and test them according to new standards which I received back from Calibration on national level lab. So we'll talk about that in a minute. I'm still catching up with some pictures. According to ISO 17025 industry regulation, or I should say accreditation compliance, calibration lab allow to, like within reasonable limits, they can allow you to be present during the calibration and also check like the methods how they calibrate your equipment. So when you order in calibration of any instrument, be it like digital multimeter or calibrator or reference standards, which was my case, then you can actually request and visit calibration lab who is doing the service for you and talk with the engineers and quality managers to make sure everything is going according to procedures and your expectations. So that's a good information to know, because I was under assumption that like even if you ship your references to high-end lab, then they will not allow you to be present. So that was a great surprise to know that actually they're required to allow you. All right. And the items I brought with me for calibration was DC voltage standard, this Fluke 732B, and also resistance standard. That is ESI SR104, legendary 10 kilo ohm. It's this box. So it's nice wooden box with the oil-filled container inside, completely hermetically sealed, and it have wire wound 10 kilo ohm resistor. Very stable, and this box is over like decades of use. They drift very little, so that's what's special about them. And each of these resistors, they come with the certificate on the lid. So let me, this is mine, and it was, let me show. As you can see, there it have all the temperature coefficient data, and year of manufacturing, and also the temperature coefficient curve. So the temperature test range for these resistors are from 18 to 28 C. That's the metrology environment. And then you can also see on this sticker over there, it says 00 ppm deviation, and the calibration date 30 July 2003. That was made before I bought this resistor. And I had actually calibration report from 2016, and also now I have new calibration report from last week essentially. So that's the box, and there is one side, this is the resistor, so you connect your measuring equipment over here, and this is the temperature sensor for the compensation of internal temperature in the oil tank. And there is also thermometer well. You can put the like a SPRT probe and have another temperature reading on the end of the oil chamber. So this is currently ESI was acquired, the company who was making this resistor. ESI was acquired by Tegam, and then later Tegam was acquired by EAT. So they are still manufactured today. And you can buy actually one of these resistors for your metrology lab for calibrations and any other purposes if you need very stable 10 kilo ohm reference standard. So the price is not cheap. It's like, I think if you buy brand new, it's over $8,000 US dollars, and that's why mostly you see this kind of standards only in high-end labs. And as of DC voltage, Fluke 732B is the typical standard used for these applications, and it's replaced today by 732C, which is essentially the same specification unit, just have additional 0.1 volt output. But I have still the B version, the previous one, and it's right over there, second in the frame. So that's in the corner is prototype, overnight resistance standard for 1 ohm and 10 kilo. I have covered more information about it, including the teardown, in article on xdevs.com. You can go xdevs.com article /FSL 935 to read more about that resistance standard. So now I want to show you the lab where I brought all that stuff. And let's see, so this is the calibration lab, and this is the PGVS voltage reference. It's a national standard here in Taiwan. So I'll go over details of the system. Like you see my reference DC voltage source in front, sitting on Pelican case, which I use for the transport, and also that white box is my SR104 resistor, which we talked about. And in the background you can see that tall rack. That's essentially all the equipment necessary to run Josephson Junction standard, which is cryo-cooled chip, semiconductor, superconductor actually chip, which sits inside the helium tank. That's 100-liter cryofab helium tank filled with liquid helium at minus 273 or thereabout degrees. That's Celsius. So that's around 4 Kelvin. And this system is built by NIST. It's you can actually go to NIST website and search for Josephson Junction standard, and you can find more information about it. So it's a very expensive piece of equipment which provides ultra stable, intrinsic voltage standard, so it doesn't drift over time, and the accuracy would be limited by your DUT, connected DUT, because there is also like all the references, even like Zener, the very best one, like this Fluke unit, they all have some amount of noise, and that noise is what will be limiting short-term stability, and the drift over time will be determining long-term stability. So I can show, this is a new system, it's programmable chip. So here is another picture of it. Let me see, I can go over each of the pieces in here. So we have probably the most cheap piece of setup is nanovolt meter. That's a HP and Agilent 34420 nanovolt meters. They are used to measure the difference between the standard you connected and Josephson reference. Then you have NI bias source. So those are multi-channel DACs connected to the custom box over there that will bias the chip with the current, so you can select on which voltage point you want to do the measurement. Then you have the data-proof DP320B scanner. This is low thermal, high quality switch, which will allow to scan you multiple devices using the same system. On top of it, you see a small black box that is RF output amplifier, because Josephson Junction chip, it's need RF radiation to produce Shapiro steps. Then you have Agilent PSG signal synthesizer. It's generating signal up to 20 gigahertz, and PGVS system using from 18 to 20 gigahertz frequency as RF input. And then you have national standard voltage solid state standard bank. These are 6 Fluke 732Bs, and 3 of them are specially modified for 1 volt output, and 3 of others are just standard 1018 and 10 volt. So you use helium cooled reference to calibrate all of this and test them, and then you keep them running in parallel 24/7, never turn off, to maintain the second source of the volt. And then you have 3458A on the side, so that is all usual. And then the helium chamber, helium tank, have their own cryoprobe. So you can see the RF input goes on the front, then you have DC block, then you have custom filter blocks. You connect all your biasing signals input through this DB style connector, and then you go down into the helium tank, and currently it's around 70 liters. So it's enough, like this 100-liter tank is enough to run the system about, they said, like around 3 weeks. Then you need to refill. And then the gas return is this hose for the helium recycle system. And we can take a look on how all this works in this poster. So it's essentially a picture of what I already covered: voltmeter, bias source, scanner, microwave source, cryocooler dewar, and then the whole arrangement is in block diagram, schematic diagram. And then the quantum chip, superconductor chip, is this small PCB over there with the silicon, or it's actually superconductor metal junctions. And then depends on what's the bias current, you will have different output voltages, and this is the difference from the conventional or older GVS systems. They provided you fixed steps, and you had to jump into the specific level, and then you compare your external DUT to that level. And the program will allow you to do the programming in determined steps. So you have here different curve, but the idea is actually the same. You need to stable voltage over different current to compare it with the device under test. And then you have here also features comparison between CGVS, the older generation systems. They are able to output from minus 10 volts to plus 10, working with frequency around 75 gigahertz. They have 20,000 superconductor junctions, and they are driven by voltage and can output only DC voltage. But the new PGVS system allow to first work with lower frequency, so you don't need to have more expensive microwave equipment to get the 75 gigahertz source. You can just use a synthesizer like that Keysight/Agilent PSG to generate lower frequency. And then because you have the current driving and you have more control over the bigger amount of junctions, you also can generate low frequency AC, like from DC to AC, like this table shows below 500 Hertz. And then if you compare directly Josephson standard against DUT, the best uncertainty you possibly can get is 9.8 nanovolts per volt for 10 volts and around 15 nanovolts per volt for 1 volt, 108 HIM. That's already with the card band K2 and confidence level 95%. All right. Now we can also take a look on another poster. So this is how the comparison system works here in National Lab in Taiwan. So you have a DUT device, for example, a voltage source or voltage meter, which measures or sources from 1 millivolt to 1000 volts. And that can be compared using the divider, like Fluke 752A, using the null detector to 10 volt reference. Then you can also, if you go higher in the chain, you can use voltage standard to calibrate. So here, lab in Taiwan actually can do two types of service. One is compare your voltage standard to their solid state voltage standards, which is mostly used option because it's reasonably affordable and you don't get that much of the difference for the everyday calibration lab purposes. But you can also go higher in the chain, that's what I did, and use your voltage standard calibration directly against the Josephson junction standard. So that it is almost double the price, but you get direct comparison to SI volt. How this works, like most of the countries, if not all, they will have international comparisons of their GVS systems using transit standards to ensure that voltage measured in Taiwan is same as voltage measured in Japan, same as voltage measured in Korea, or in US, or in Germany, or in France. So the international community, metrology community, it's like BIPM and working groups which are working around this. They handle those international comparisons over the span of time, so they can get accurate representation of the volt no matter where you are in the world. And there was a question about using PXI system. Let me find a picture of that. So I think we can use this one and go over again the equipment use. So yes, this is National Instruments NI PXI 1042Q. That's the mainframe. And you have the controller computer over here. And you have timing module. And then that is multifunction DACI. And the models are for the module are NI PXI 6652. And then 6 units of NI PXI 6230. M series multifunction DAC, and all that is connected to inputs on this custom box GVS 650 Josephson bias system. And then the output, this Teflon insulated cable, goes into our nanovolt meter. Okay. Hopefully that should explain what they use. And also they have older system, which is CGVS, which was retired in 2015, replaced by the new system which we just looked at. And right now it's turned off. So you have the frequency counter to monitor the input 10 megahertz reference. Then this is the EAP 578B, that's the lock-in microwave counter. So with this coax wire going to the RF source. And then they also have as a frequency reference Symmetricom rubidium source, model 8040. So that provides essentially the time reference for the GVS system. And then this is the older gear for old CGVS chip, so similar idea, bias source. You drive the old chip with the voltage, so you don't need 16 channels of current source. That's why it looks like much simpler, and it's GBS 500 bias source system. And the Tektronix oscilloscope is used for controlling the steps. And microwave section of the CGVS system is this piece. So that coax going in here, this is mixture for 75 gigahertz. So it will look into the waveguide 75 gigahertz output of this gun diode from Militech, and it will adjust the bias for the gun diode, so you get precisely stable output voltage, output frequency. Sorry about that. Then you have attenuator, mechanical attenuator with waveguide VR12, and it's connected to this flexible waveguide hose. Right now there is no connection because the system is not used. You can see the plastic protection cups on the waveguide output. And then the old Duor is also cooled by liquid helium, similar 100-liter tank. And then that microwave input goes into this cryoprobe. And it's interesting, there is a low thermal Keithley short, model 488. I actually use one of those on my Keithley 182. So that's the older system. And GVS system supports only output for -10 or +10 volts, and programmable in between. But if you want to compare higher voltages, then they would use Kelvin-Varley divider, like this EAT KVD 700, which is essentially the same spec and same feature as Fluke 720A. Or if you just want fixed 1 volt to 10 volt, or like 100 volt to 10 volt, or 1000 volt to 10 volt, with better stability and accuracy, you can use Fluke 752A, which is this box down there. Then they also have some auxiliary standard, like this Datron 4910, bunch of nanovolt meters, like this one, and that one. That's Keithley 155. I have one of those as well, sitting on top of the equipment. And the reason why you want to have a nanovolt meter, null detector as Keithley 155, is very high sensitivity. The lowest range it can go is 1 microvolt, compared to what typical even high-end DMM like 3458A would do, only 100 millivolts. So, and also it have Keithley 155 have battery power, so you don't have current mode errors from like AC pickup or noise pickup from the power line. And then the alternative is also to use Keithley 2182A. That's the modern nanovolt meter, but actually the results are better with this old school, but still very capable, sensitive 155 units. And this box with bunch of binding posts, this is very special bit of kit. It's Datron 4902S, essentially a passive resistor divider, which can divide up to 1000 volts with very good stability. It have hundreds and hundreds of Vishay VHP hermetic resistors, and it's have very good stability, and also all the sections are guarded. So there are actually 2 dividers in one package. One is working divider and one is guardian divider. And of course we can see some multifunction calibrators, good old trusty Datron WaveTech 4808 and 4708. So I think this should cover the voltage measurement. And this is another picture of the solid state national standard here in Taiwan. Any questions? There are a lot of information in even just looking on these pictures, so I wanted to cover as much as possible. But if there are any questions, I'd be happy to answer, because the next step we're going to take a look on the resistance. So there is one particular interesting slide. All of this, like why would I pick the time to do the calibration for my standards now, is there is one reason for that, and that is SI unit redefinition, which happened over last and this year, but come into effect in May 20, 2019. So the most important and significant was redefinition of a kilogram, but some of other related units also redefined. That is ampere, and I think temperature also redefined. So why it's important to, in terms of the calibrations, that ampere defines electron charge, then you have voltage from Josephson junction standards, and then you have resistance. So you have this triangle from the Ohm's law. You have voltage, and current, resistance, and we have quantum realization of voltage, quantum realization of resistance. It's defined now from physical constants and not defined from human-made artifact. So essentially you can, if you explain the definition to anybody in the world or even outside of the Earth, like for some Martian metrology labs, you can define, okay, like the voltage 1 volt is this amount of units in relation to physics, physical constants, then they will understand what you're talking about. And this is how everything interconnected together, so-called quantum metrology triangle. And because of the redefinition which come in effect on May 20, we have voltage changed by 106 nanovolts, if I'm correct, and that would mean if you have calibration against the Josephson junction, your calibration value will need to be adjusted and changed. And all the metrology labs were doing this adjustment and correction on that date, and from every day forward, now we will have updated values. Now you would ask, will it matter if you just use normal benchtop DMM and send it for calibration? And the answer for that would be there would be no difference, because typical, even very nice quality benchtop DMM does not have enough stability and sensitivity and resolution to actually should distinguish that 100 nanovolt or 106 nanovolt change. But if you actually send in high-end DC reference like Fluke 732B, and you doing the comparison directly against the Josephson standard, then you would see the difference, and that would be important for high-end calibration laboratories, which will provide you accreditation values. All right. And the question is the new standard of SI for mass based on microwave measurement. Well, there are two realizations of new standard of kilogram R, and one is SI kilogram represented by silicon sphere, and the second is Kibble balance, which is using Josephson junction to measure to have the relation to voltage and also current quantum realization for measuring the power for the magnet. So essentially you have physical weight compared to electrically controlled electromagnet weight. But that's a little bit outside of the scope because I don't do any dimensional mass calibrations. So far I'm limited only to voltage and resistance. Perhaps that would be a good topic for another video. So let's take a look on the resistance quantum reference. This is not well, it's still liquid helium cooled, but it's not using Duor, which need to be refilled every time, but it's actually using cryocooling system. So you have like in that thing on the background on the center tank, that's the dual stage pulse tube cryocooler. So it's in the very simple way, it's working like a refrigerator you have in your kitchen to store food, but instead of cooling to around 0°C, this device using helium to compress and displace gas and cool first stage to around 70 Kelvin or like 60 Kelvin, and then that stage will cool the second stage down to 4 Kelvin or even lower, like 2 Kelvin, which is in turn attached to quantum Hall effect resistance chip. And then the whole thing is vacuum sealed. You have two vacuum pumps, very expensive high vacuum pumps that will remove all the air out of the chamber, so you don't have condensation or like water vapor or any other particles corrupting your very sensitive equipment inside. And then quantum Hall effect realization also using magnetic field to produce fixed step of resistance, which you can read back. And this large tank on the left side is the helium expansion tank. And all this together works to provide you 12.8 something kilo ohm, which we can take a look over here. So that is how this works. So here's the steps we have. So for magnetic field between 8 or 12 Tesla, like with the sweet spot around 10, you get a realization of 12.9064035, and actually there are 15 more digits. They're just not represented here for simplicity. That is fixed resistance, and you can compare another resistant artifacts to this value. And then the whole physics and structure. This is also superconducting chips using some special materials. And actually Taiwan lab, CMS lab here, manufacturing their own quantum Hall chips. And some of these are shown here on the photo. So they are not just using industry recognized chip, but also manufacture their own. And then this is how the comparison works. You have DCC, direct current comparator resistance bridge, which will compare cryogenically cooled QIHR to the standard resistor like my ESI SR104. And uncertainty of such a transfer can be as low as 110 minus 7, so that's 0.1 ppm, or even better. And you also have a lot of physics involved in operating this device. And I have I think, yes, this picture. So they use Lakeshore cryogenic temperature monitor to display what's the temperature on each stage. So you have first stage 54 Kelvin, that's lower than minus 200 degrees C centigrade, and then you have the second stage working around 4.6, 4.8, depends on different probe locations, and this temperature is all in Kelvin. And then you have the controller, PID controller, to heat up or cool down the chip to around temperature they set as a desired. And then the whole controlling box is this unit. So you have the software to monitor all the parameters of the system, and you have those thermometers and temperature controller, some industrial computer that controls all that, and magnet power supply. So this rack sits next to QHR system. And then, okay, you get this 12.9 kilo ohm resistance value. What you do next? Well, next you compare it with the resistors cooled by oil bath, or I'd rather say kept at the stable temperature. So here you see 25 C, very stable, very accurate temperature. This is Measurements International, very famous calibration equipment supplier. Usually they are very expensive, and that's why you see them mostly in big like national level calibration laboratories. So this is oil bath, which have all the various primary standards like 1 ohm, 10 ohm, 100 ohm, up to hundreds of kilo ohms, even mega ohms. And then outputs are connected to the DCCT system, which is these large two racks, and the main piece of equipment is this Measurements International 6010D. This is essentially a comparator which allow to give the ratio of a known resistor to a known resistor, or in this case quantum resistance output to one of those primary resistors in the oil bath. And you can think of it as a 11.5 digit resistance meter, because the ratio can be determined very accurately, so you have this crazy resolution and extremely high stability. Then you have a low thermal scanner, so this is a switch to select which resistor you want to compare to. It's a model MI4220A. And also, if you want to measure very low resistances like 0.1 ohm or like even 0.01 ohm, you would need high current, so you can get lower noise and accurate readings. So for that they use 150 ampere range extender, and also the DC supply, low noise supply, and some heavy gauge wires to measure low resistances. An alternative current source is this key side. This is model 6680A. I think it's 875 amp DC supply. And then for even higher currents and even lower resistances, they have second supply like that, and then 3000 amp switch. These wires are like 2 fingers thick, able to carry 3000 amps. And this is 3000 amp reversal switch, because you want to measure in positive and negative polarity, so you also need to reverse the current, so you can cancel thermal EMF and errors from the voltage offsets. And then there is an alternative unit, 6014M, 3000 ampere range extender. Just look at those wires. The cross section is 325 square millimeters. So that is the resistance measurement rack. It's very expensive, and for the high resistances another system would be used, like this box, which is high resistance radio bridge. So it works the similar way as the previous 6010D, but instead of using high current or lower current, this uses voltage. So there is voltage extender, voltage sources, these two boxes, 1000C model, from 0 to 1000 volts. And essentially they form a voltage divider using calibrated high resistance references, and then they can determine unknown resistance. And for example, in here on screen you can see readings up to 8.5 digits for resistance measurement. And then next to this box is temperature controlled chamber. So you want to keep the temperature of your device under test very stable, so there is no temperature coefficient error, and that's why they put in this oven type box, which will keep the program temperature very stable. And that is high resistance standard. You can see type N connectors as the input and output, fully guarded and set on the Teflon insulated sheet. This box allows resistance output from 100 mega ohm to 10 tera ohm with steps, 10 decade steps. And they also have some guideline 65A tera ohm meter, another high resistance meter 6650 AF, and of course there you can see the piece of another 3458A there. And let's see, I think there is one more picture. Yeah, this one. And this is the older oil bath. So this is a retired system which had a little bit more stability. It's guideline oil tank. It's very huge, all in heavy wood walls to keep the temperature variations inside the oil tank as small as possible. You can see some 1000 amp wires. This is, I think, SR104. And here is the current shunts. Very serious currents. Very serious weight as well. This thing is huge. You can see the normal office chair compared to the size of the oil bath. All right, lots of fun. Okay, so for the resistance, for the temperature monitoring in the oil tank, they also have secondary guideline 94. I think it's 9640 or 9540. I'm not very familiar with this guideline thermometer, but it's essentially 1 millidegree centigrade resolution thermometer. So what else I have missed? I think I covered everything. Also there is older quantum Hall effect standard, which they used years ago. This is liquid helium cooled one, and as you can see, it was made by Oxford Research Instruments, and this one is cooled by liquid helium. It's not a cryo engine cooled. And the related equipment for it, that's the vacuum pump, helium pump, all that. This is a retired system, so they don't use this anymore, but it's still functional. Probably they can use a new system and old system if they want to compare different quantum Hall chips to see what's the correlation between them. And there is also AC voltage lab, so we can touch a little bit on that, but I think I'll be doing AC voltage calibrations in future, so we'll definitely dig into that topic sometime later. So there are typical workhorses of AC voltage lab, such as Fluke 5730A multifunction calibrator. This is a high current amplifier, Fluke 52120A, and then you also have AC voltage measurement standard, which is this 5790B. And then some device under test boxes. But the main standards are this very expensive shelf. So you can find thermal voltage converters, because this is essentially what is providing the best accuracy and best stability for AC voltages, other than quantum realization, such as Josephson arbitrary waveform synthesizer, GAVS system. And the second best is the thermal converters and thermal converter based instruments like Fluke 792A and like this TVC element. So you have different element for different voltage, like this one. Can zoom in a little bit higher. So this one 1 millivolt, 2.5 millivolt, 5 millivolt, 10 millivolt, 50 millivolt, and they go up to like 100 volts. And it's important to use the correct TVC for correct voltage, otherwise you will blow it up and all your years of measurements and history will be gone in an instant. And also for the AC shunt, you would need AC precision current shunt to measure AC currents. So there is a fleet of Fluke A40B. These are tested and calibrated by Europe Lab PTB. It's in Germany. So there are different shunts for different currents as well. A40B set. You can see they also have labels 10 milliamp, 20 milliamp, 50 milliamp. And there are even bigger ones, like in this corner. That's for I think 1000 amps, 100 amps, using LC connector. And some more of the TVC and bias tees. And this is the reversal switch for the 792A. Just that shelf alone, in terms of cost, probably cost over 100,000 US dollars. And this is, for example, one of the rigs used for measurement. So you have calibrator source 5700A with the 5725 amplifier that will provide stable AC voltage or AC current. Then it will be supplied to device under test and will be measured by the TVC element, such as here you can see TVC element with the current shunt attached to high current scanner. I think this is one of the older Keithley scanners. And this is another Fluke current shunt, Y5020. And as a detector DC voltage, because how the TVC works, it accepts AC input, converts into the thermal signal, thermal heat essentially, and then the thermocouple or the thermal sensor inside the same package as the TVC will sense the heat and provide you DC voltage. So why it's important is that you don't have the error from distortion of the input signal. So if you supply sine wave or triangular wave or even some AC voltage which have noise on it, essentially any waveform, then it will be all the energy will be converted into thermal, so you can get accurate RMS output even if your signal shape is not perfect. Unlike the digitizing methods, this can support crest factors which are much higher, and that's why it's mostly used for metrology purposes in calibrations. And that DC output voltage from TVC element is matched by long scale DMM, like this Fluke. This is Datron 1281. It's essentially used here just as a simple voltmeter, or as alternative Keithley 182, that is nanovoltmeter with the lowest range 3 millivolts. Alright, so that is I think that covers all for Taiwan National Measurement Laboratory, which is located in Hsinchu. That is same city as TSMC. You probably know TSMC semiconductor factories. They made a lot of mass market chips, such as NVIDIA GPUs, AMD stuff, and many of Apple SoCs and devices, and many other things. One of the leaders in the history. So I went, I hand carry all my standards, well, this 732B and the resistance standard to their lab, because I didn't want to risk shipping damage or like having the standards sit in the warehouse. So that's why it's important, especially for the voltage solid state references, such as 732, it's important to keep them powered on all the time, so you don't have the temperature stress or temperature hysteresis induced to the Zener output voltage. So they also have battery inside the unit, and that battery can support operation of the oven and the Zener output up to 72 hours, or if you use additional battery pack like 732B 7001, then you can extend the whole time of the Zener operation up to around 140 hours. So that's enough to do a cross ship, like fast cross ship inside the country, or like in my case, just enough to carry the standard, because it's only like 1 hour drive from here, from my lab in Taiwan, in Taipei, to lab in Hsinchu. And I calibrated my references, so now that I know the exact value of standards with very low uncertainty, so I can take the value and use it to adjust my DMMs, my calibrators, and my other voltage standard which stay in this lab, and I can compare what's the error from correct SI volt transfer to my internal XDEV lab volt and resistance transfer. So right now I have actually calibration already done on these 2 meters. So these are my main, let me zoom in so you can actually see what's going on in here. So right now there is a test running. I use this 5720A calibrated against 10 volt from 732B, then against 10 kilo ohm of ESI SR104, and for 1 ohm I used my last year calibrated SL935, this guy over here, and all that was used to adjust all the ranges and all the functions of calibrator using artifact calibration procedure. Then I used 10 volt, same 10 volt reference and 10 kilo ohm to adjust this guy and that guy together. And right now you can see this top meter is just reading the 10 volt directly from the reference, and the bottom meter is connected to calibrator, running through all the tests. So I have the Python script which programs the calibrator to specific points. Like right now you see 0.3 volts, so 300 millivolt, 20 hertz, and it output into the meter, and meter measures AC voltage. So it will go through different frequencies for each voltage point, and also it will do other tests like resistance output of the calibrator and DC voltage output and DC current, like using the amplifier output for high voltages. And all that will be monitored by the Keysight 3458A, and we will get the final report with the calculated deviation between this guy and this guy. And because of the artifact calibration, we should see, given that this instrument is working correctly and in spec, and given this instrument is working correctly and in spec, we should see agreement for less than 24-hour specifications. And my previous, I actually have had a sticker which I need to update. My previous calibration date for this meter was January 4, 2017, and this meter was calibrated. Let's see if I can actually no, and report the calibration string, I think. I think I should be able to, yeah, no, it's only GPAB command. So this meter was calibrated in 2018, and I was able to determine that both of these from previous transfers or from this transfer, both of these actually drift less than 2 ppm for a year, because I know the previous value, I know now the current value, and I can calculate the drift on 10 volt range. Essentially the drift of the own LTZ 1000 reference inside the meter. These meters are never turned off, they always running even if they are not measuring anything, just running to keep the stable temperature and stable conditions. And then the next step would be this test, like the whole setup. I'll first get the report on this unit, then I'll switch the cables and test the top meter, and they should agree to each other very well. And then we can also do other tests using other equipment, because I still have 2 more meters to verify, like this one and that one. And actually this bottom unit will be available for sale. I'm going to list it for sale next month. I already have enough 3458As, and actually I have some more exciting equipment coming in soon. With help of our US lab team. So I'll not have need for 4th 3458A, that's why it have to go. So obviously it will be fully calibrated to its 24-hour spec using now national level standards. And the price would not be very cheap for it. Just a fair warning, if somebody think that you can buy a cheap 3458A, that usually is not the case, because even if you manage to get a broken one for reasonable price, you likely will need to replace the expensive ADC, which are hard to get by. And like I had 100% luck with my units, meaning that all of the 3458As I bought, they all needed ADC replacement. And as you can see, now we have next step, 40 Hertz. So the whole test taken about 15 hours for one run. So you can count, I have 4 meters and each of them will be 15 hours, not counting for the like wires change or like settings check, stuff like that. The idea of having multiple meters is the key importance, because if I have just one meter and one calibrator, like even if the readings are agree to each other, I wouldn't know if it's still correct or not. Otherwise, like for example, if this drifts up 10 ppm and this drifts up 10 ppm, they will agree to each other very well. But actually the total error to real voltage or real signal would be error 10 ppm. But because I have multiple of them, and if they all agree to each other and also agree to the standards, which I have calibrated less than 10 days ago, essentially the calibration date was May 30 for resistance and June 3rd for resistance and May 30 for DC standard. And then I'll be using the second calibrator. It have limited function because it have don't have the high voltage output and high current output, so it only goes up to 220 milliamp and up to 22 volts, but otherwise all the other functions are still there. So this is my secondary unit, which I'll be using as a current source or as a DC source for low voltages like 22 volts, 11 volts, 1 and millivolts. So this is fully functioning calibrator. As you can see right now, it's actually measuring AC voltage, output AC voltage signal, 1 volt, 1 kilohertz into my AC voltage measurement standard, which is WaveTech 4920M. I'll be posting the reports and results and actually full article about everything I shown and discussed in this video on xdevs.com site. And I'll probably will update the link to the article in description of this video. And yesterday I calibrated the unit using my Keithley 155 and using Fluke 752A, which was very tedious process. So this little guy, it's very handy little meter. Also, like if like you don't actually need to have such a high-end equipment if you're just doing the hobby work, but for me getting the calibrator like this 5720, the main purpose and main reason is that it have artifact calibration function, because I don't have that whole set of TVC elements, then whole set of the voltage sources otherwise to measure and accurately calibrate the calibrator. Some gunk in here. Calibrate a calibrator like 4808, which you need to manually test and check and adjust every single range. So having 57 series calibrator actually helps to remove all that, and you can just use 10 kilo ohm, 10 volt and 1 ohm to essentially self-adjust the whole unit. There is a little side note though, that you need AC voltage reference to ensure that AC function works correctly. That's why I got this WaveTech 4920, which is similar unit to 5790A or B, with very comparable and capable specs to test calibrator. And I adjusted my 4920 according to 5790A back in November 2017, and it's working happily since then. But actually I do need to test and adjust AC voltage functions for this standard again, to ensure all the ranges and all the functions are in spec, because back in when I was doing this in November, I didn't have 5725 amplifier, so I couldn't go for high voltage and high frequency points. So it was without the amplifier, this bottom box, a calibrator can only source up to 1 kilohertz for 750 volt output. But with the amplifier, you can go down to 100 kilohertz. I'm talking about this 5725A. All right. And the second step would be, well, I would rather say next step. Now that I have SI volt in my lab transferred by sub ppm accurate reference, now I can adjust and do the final calibration for all those XDEFs, FX 10 volt LTZ 1000 modules. So I will be shipping, preparing and shipping them within this month to all our EEV block Metrology forum section members. And then the next project would be going back to my other neglected reference, which sits right over here. This is WaveTech 7000 LTZ 1000 based reference. It just sits unhappy, open up like that, powered by Keysight E36312A. And I would like to give credits to Keysight for this power supply. It's a great unit which I use daily as a voltage source and power source for my experiments. We have much more projects in the loop, like those 720s still need some attention. And then some ratio bridges. And of course, our new fresh addition to the pack, that is auto balance AC/DC transfer standard, Valentine model 1605B. This is a very special bit of kit. It is essentially Fluke 792A, but with the ability to go up to 100 MHz in frequency. And unlike Fluke AC/DC transfer standard, this one have GPIB, and all the ranges can be controlled remotely. So I still have some work to do on it because the connectors are really in poor shape, but the replacement is already on the order, and hopefully we'll have it completely working and happy to go in no time. And here is my secondary reference that was sitting in the lab all this time. So this is a Fluke 792A power pack. It's essentially a box with a charger and bipolar ±11 supply, which have XDEV's FX LTZ 1000 reference, and I modified it to provide output using low thermal binding posts with the Kelvin output connections. And then we have good old 732A. So there you have it, little tour. Okay. And also I wanted, after the test on the calibrator is done, I'll be doing the calibration for 5450, this box down there. It is a resistance standard and can supply outputs from 1 ohm to 100 mega ohm in both step 10 decade and step 1.9 decade. So it can supply like 10 kilo ohm, for example, like that, and 19 kilo ohm. So in the function wise, it's similar to what 5720 supply, but actually the stability of this unit is better than the calibrator, because calibrator is using thin film networks. I can actually show you board. So this is a resistance board from 5700 calibrator. in focus. As you can see, it's have a lot of relays for do the Kelvin connect switching, and it's also missing one of the resistors. That happened because my main board in the calibrator was damaged during the earthquake. It's actually cracked in half, so I had to buy this donor board and take the resistor out and replace the one in my board. You would ask why I don't replace the whole board, just take this board and install in the calibrator. Well, because I already had the measured and log stability of the previous board with other resistor networks over more than a year, so I didn't want to lose all that, so I just replaced the resistor. So this is from 5700A, and unlike this board, the resistors inside 5450, I'm sorry, all these numbers. Inside this box, they are all hermetic sealed wire wound resistor, so they are more stable over time and also can survive more current. Server rack, there is a question in the chat box. Don't I think about server rack to mount all this stuff in it? Well, the problem with the server racks is the size. If I'll mount everything into the rack, this would be at least battery is off. That would be at least 4 full-size 42 unit racks. And the problem with the racks is I don't have much space in here. This is a rental apartment. And the second problem is, okay, this is battery dead too. The second problem is thermal management. Because you can see I located all the sensitive stuff on the left side because there is no vent hole in the calibrator from this side. So there is no airflow from this side coming that could disrupt any of that equipment in there. But the vent holes are from this side, so the hot air from the calibrator, it's sucked from the back and then it's blown by 2 fans in this direction. So all the exhaust is in here, and then it goes up, and well, it hits up these meters, but these are not my metrology important meters right now, so that's why they are here. So you need to think because like why that is important. Like if your temperature in the meter change for even like 2 degrees, then your readings would be also subject to the temperature coefficient of the meter, and most of the meters, they will have some error. So the bigger the difference you have from the calibration temperature, then the bigger the error is. Yes, of course you can measure what the difference is and then compensate for it doing some mathematical equilibrics, but it would be just easier and better to remove the problem instead of trying to work around of that problem, of course, if it's possible. So in the rack you would have denser setup, and you would also have less air space to breathe unless you add more fans and cause more noise. You can show the overall lab again to give you the impression like that this is not a big place. So I occupied the whole room just for the equipment. So this is it. And then that's the entrance door and the wall. So this is, I'd say, maybe 4 meter by 2 meter. And then you have the aircon over there, which is forever turned on. Otherwise all this lab will heat up to 33-35 degrees very quickly. And then some lights to provide some coverage for video. So essentially I have a chair there for a table to work on, and not much else place to be. So first I'll have to upgrade my location, and then we can talk about racks. Hopefully that will happen sometime next year, but we'll see about that. I also have another room where is my main workstation and my other stuff lives. So that's not the only room in the apartment. Otherwise I wouldn't be able to dedicate the whole room for the equipment. So another thing I wanted to cover is what's actually the difference before and after the calibration of my meters. So let's take a look on that. Let me prepare some data, and I could show some graphs. This will take just a minute, because all my data logging is stored on FTP server, and then I have plots that are redrawn every 5 minutes. So even if I'm not in the lab, I can use smartphone to check on how is the measurement going and make sure everything is okay. So I'll just show that in a minute, and we can go through the data. But first I need to find the data. I have so many of these charts that sometimes it's a little bit tricky to get everything correctly. Okay, I think I got it. Okay, I don't have the graph which shows after the calibration. I have the one which shows before, so I can display the error. Let's do that. Yeah, I think this graph will do. Let me change. Oh, this doesn't work. Huh. Okay, that is interesting. Okay, now this works. So here is the thing. On the graph you see a lot of lines. So let me go through each one of them one by one. So you can find this page if you go, well, I'll post the link in the description below. So what you see here is the most important scale is on the left side, this ppm scale. So the vertical, the whole scale is from 1.5 plus 1.5 to minus 1.5 ppm, and this vertical scale is in voltage. All the lines are scaled to the same axis, but the absolute value is different. So that's why you only use ppm scale to find out what the deviation is. And the measurement in this graph is 732B the next day after the calibration. So I input correct 0 ppm value from calibration report, which is this 10.000015. It's actually 1524. That is our reference, measured by National Lab in Taiwan for the DC output. And then I have multiple meters measuring this output. So you can see they are depicted by different colors. So you have 3458A B, 3458A. These are two units which sits by the right side of the calibrator. And then we have 3458A C, 3458A D. Those are the two which sits by the left side of the calibrator. Then two of my Keithley 2002 units, the green and red. And then you have Fluke 8508 measuring in ratio mode SR104 to my SL935 reference. So the calculated value is for the SL935, so we can ignore that. That's the brown line in the center. We can ignore that for a second. So where we can start first, we can take a look on 3458A ref, which reads as 10.0. This is median output reference. So this is the thick dark blue line right over there. And actually we also have the temperature log. This is the temperature. It's on separate chart. But in average the temperature change from 22C to 26C. So for the actually like the temperature impact affects 3458AD, 3458AC unit, and also Keithley 2002-6. 6 is GPA B6. So we can talk about that in a minute, but let's go back to our dark blue. That's the 3458A. The one which is actually right now tested by the 5720. So here we can see at the start of the data, our error was minus 0.6 ppm. So remember, this meter was calibrated in 2017, and from 2017 it's like together with the error of that calibration and all the drift and everything involved with this meter, now we get the reading from the 732B reference only less than 1 ppm. And then if we even go to the worst case, like this point, then it translates to minus 1 ppm. So I'd say that is very impressive for the home lab, which doesn't have strict temperature control, which doesn't have like any special like measures to control humidity. Essentially just a private lab with a bunch of expensive equipment in it. So the second meter is even more impressive. The B unit, this one was calibrated and adjusted in 2018 by my friend Todd in US. So what happened, I bought the meter and shipped. It was located in US, so I shipped that meter to US, and then he tested it and adjusted it. But actually I'm a bit misleading you, because this is not just the direct meter output. This is the difference measured by yes, this is 9999779. This is my second reference differential to the 732B, and it's digitized by 3458A, which measures Keithley 155. So actually that's why you can see the noise is less than 0.1 ppm. It's much less noise than normal 3458A, because it's actually not 3458A reading but Keithley 155. See, I already even forgot what this was. Now I remember. And so this is difference between reference that I ship to Taiwan lab and the reference which sit at my house. And that reference is 9999779, and that's exactly what it's have before the sending. So the difference is 34 microvolts, and that's what we get. So let's go to the green one. So green is Keithley 2004 GPA-B4, and it reads 0.7 ppm, like plus 0.8 minus 0.5, so that's plus minus around there. I'd say an average is around plus 0.65, and you can see it doesn't really affected by temperature, even if we have the big temperature change. Well, it's just small change on the output, so this is meter very stable and very good. And the noise is comparable to 3458A. That's why I like my 2002s very much, and I'm not planning to get rid of them. They are my secondary meters, which I use for DC and resistance measurements. But we cannot say the same about the GPA-B6 unit, which looks like it started better. It's only minus 0.4, but it's actually go down to minus 1 because of the big temperature change. So it's affected by temperature much more, and I'll actually have a look on if we can improve this. So I'll have to measure what's the LTZ output deviation in this meter. Because remember, all the 3458As, all the Keithley 2002, they use the same reference, so essentially the stability of the long-term stability of the reference is the same. Then we can go back to 3458As, C and D units. That's the unit number 3 and unit number 4. And you can see they still around all of this. Like the worst case, if we take like this is 3458AD, it goes up to 1.2 ppm up. And then the lowest one is 2002-6 minus 1.2 ppm. So even I have 6 different meters, they all agree to each other and agree to the reference, which is more important, agree to the calibrated reference within 2 ppms. Much within that. And this gap on the end is because I actually stopped the measurement and did something else, so the reference was not connected during this time. Actually, I was doing the calibration on the calibrator in this hour, and then I reconnected everything back, and that's where you see the continue the data back. And then humidity, average humidity was around, the humidity is this thin brown line, around 22%, with the peak up to 33%, so the humidity is low. And the pressure is around 1000 hectopascal. We can also see the temperature readout of the 3458As, A and B, It's around 39, and the second unit is 41C. Those blue lines in there. And this graph is available. It's a live update graph. Was recorded just day before yesterday. And let's see. This is the graph. Okay, any questions so far? I'm still actually testing some of the references I have, ADC boards I have for 3458A. So hopefully I'd be able to improve that temperature stability of the C and D unit, so we don't worry about the temperature coefficient. And all this time we were talking, and you can actually, I can try to show, just to indicate that metrology is not a hobby for impatient people. All this time which we are talking, and the 5720A is still only 100 kilohertz point, and on the same voltage 300 millivolts. So it will step through 10 hertz, 20 hertz, 40, 100, then 1 kilohertz, I think 5 kilohertz, 10 kilohertz, 50, 100, 200, and 300, 500, and 1 megahertz. And do that for all the low voltages up to like 100 volt. And then for the higher voltages, the frequency will be limited to less values. So right now we can see, I can go, spec is 200 ppm for this output, and our meter right there, well, it's pretty close, 300.0135 millivolts. And then we can take a look on the top meter. There it is, measuring DC reference output. So this reference output is 10.00001524, but the meter is reading 10.00000162. You would think like, oh, that's a horrible error, but actually if you count into the deviation, that is 0.22 ppms. So that is very, very, very small. And we can do actually ACAL DCV. So what this does is it runs for 2 minutes and adjusts because ADC have bigger drift than the reference, so it will adjust its own gain to LTZ 1000 reference inside the 3458A to correct for the gain error. So I think we should see closer to 152. So it runs about 140 seconds, so that's a little bit more than 2 minutes. And it's doing so for all the ranges. So 0.1 volt, 1 volt, 10 volt, 100 volt, and 1 kilovolt. So it automatically corrects all the offsets and gain errors, except the on LTZ 1000 reference drift. That's why I prefer having this function allow essentially to reduce the cost of the calibration and adjustments a lot. Because if you use even more expensive meter like the 8508, which sits right over there, that meter does not have auto calibration function, artifact calibration. So you will need to do it old school, meaning you need to connect all the outputs to the calibrator or the sources, reference sources like 732B, resistance set. So you need to have like at least 10 different resistors for each range. Then the current sources, like the whole setup to properly calibrate this meter. Like, of course, if you want legally traceable calibration, then you would need to do the same for the 3458A. But for the hobby applications, you don't need official legal paperwork. So okay, now it's a little bit higher. That's unexpected. Let's wait a little. But it's still, this is 0.3 ppms of the deviation. And sometimes there is also variation from the temperature and variation from the noise of the Zener. And when you're doing the critical measurements, it's always important to keep the source floating or like on battery power. So for that I would just slide the 732B a little bit out, so it disconnects, because this mainframe supplies the power to each of the cell, so the battery can be charged and you can run it indefinitely. I probably could try to show that. Just remove the battery charger. Let's see. I'll move everything out of the way. My lens is manual focus, so I have to readjust everything. Sorry about that. So let's see if I can show this. So this is just a battery box, doesn't have anything inside it. Just slides right off. And can see let's see. See how it's far over there. Yep, there is the guide pin and mains jack. There you have it. And then there is the hole for the connection, for external connections for battery monitor and other circuitry. And then this plugs right into the unit. And the model number for the crate is Fluke 734A, or there is a modern one which just have changed label, Fluke 734C. And that's how this setup works. Then you put the charger back in, and then it connects to the mains power and charges. The battery inside of this reference is VRLA 7 amp hours. It's lead acid battery, so it's safe to ship to the different locations and between the calibration labs. Now we measure in another step, 300 kilohertz. And now we measure in 500 kilohertz. Let me get the camera back. Okay. Any questions? I think that's it for now. I'm not sure if there is anything else I could talk about. I still have a lot of data to fiddle with and to process, and hopefully I can get some nice reports out of these two, so we can take a look what's the error of the whole setup. I'm very happy with the results so far, and finally my lab is worthy to have the standards calibrated by national level measurement lab. I never expected this to be happening, but well, here we are. I think I'm in this hobby for like, let's see, it's around 7 to 8 years. And first I just got one 7.5 digit meter from Keithley, which was broken, and I was hoping to fix it and calibrate and use it as my daily meter. But then I found out, oh, I need to have 5700A calibrator, I need this and that to do the calibration. Well, then I found another meter, hopefully in better shape, fixed that one, get it working, but they didn't agree very well. So I needed another meter, and then another meter. Then I started, okay, what if I build the reference and ship to somebody to do the testing for me, so they can ship the reference back and I can check my meter. But that will only cover for like 2 volt and 20 volt range. It will not cover for the resistance functions, current functions, all the others. That was a challenge because you don't have the calibrator, you cannot do the full calibration of the meter. And then I started working how to get the calibrator, started tinkering with some sockets, learn analog design better. Then I got some other calibrator like the time electronics. So that was actually already I have 8.5 digit meter. Because as you go, as you learn more, you want to have better tools, and as a drawback, well, or a benefit, depends on how you look at it, you will end up all this expensive equipment. I had Keithley 2002, that was my first 8.5 digit meter, but it have the same problem, it doesn't have artifact calibration, so you have to run all the points, all the ranges, all the functions against the calibrator. And I had nobody around to get access to calibrator to. So I ended up getting 3458. Actually this unit, this is my first unit. It was completely busted. It was the first article on xdevs.com. It's xdevs.com/fix/HP3458A. And you can see in what horrible condition this meter arrived. And it had blown transformer, drifty ADC. No, the ADC was broken at all, didn't even work. Then I replaced it, but the replacement ADC was drifting, and then I replaced that drifting ADC to the third ADC, which was finally good. And yeah, I spent maybe around 2 months, like 2 months almost every evening fixing this bad boy. And yep, that was it. That was 2016, if I recall correctly. Then shortly after I bought the second one, this guy. And after that everything just went like a snowball. Usually I try to avoid, like, I don't specifically buy piece of equipment because like, oh, I need it right now, so I go and buy it. That's usually not how it happens. Most of the time I see some piece of interesting equipment and the price is okay, and then I buy it. Or I try to buy it, and sometimes other people will outbid me, and then I'll save money. Which is good too. And because I know there are other people like me, like who are tinkering with the equipment and stuff, I found out that it's beneficial for the community to publish and document, like even if it's some silly, very simple issue, and fix that issue, like replace the capacitors to fix the equipment, take some internal pictures, and post an article on my website and also on EEV blog forum. And actually that helped a lot for myself and also to other people. And we get this community in XDev's IRC chat, where we share different experiences to play with our equipment, and sometimes even send references or send some meters back and forth to do the calibrations and checks. So that's how we support each other, and that's how I was able actually to get within 2 ppm accuracy for DC voltage without like shipping the meter to Keysight. None of this equipment ever was shipped to manufacturer or the calibration lab to do the calibration. We all do it in-house. Essentially, I ship like this meter come from my friend in US, and he calibrated it by doing himself, doing his own calibration to his 732B and his SR104. So this meter, and none of them never was shipped back to Keysight. Part of the reason because of the calibration cost for high-end equipment is very high. Even just to to ship this 5720 to Fluke and calibrate it to the best spec possible, that would be like $5,000 to $6,000, and that's not even covering the shipping cost. Like this is 30 kilogram unit, so that's like 90 pounds. Shipping from Taiwan to US, 90 pounds, that's expensive. And then you also need to ship it back, so you're paying for shipping twice. That's why I like artifact calibration so much, because you can do calibration to very good level, very high standard with these meters and with these calibrators and these meters. Just having like I can take that standard and my resistance standard just in two bags and carry them into the lab and calibrate them, and then bring them back and calibrate all the equipment. So in a way, it's saving a lot of money, because otherwise I will need to ship each one of these meters to calibration and pay essentially 4 times more than I would pay for the calibration and the SR104 reference. Even though I had to buy a special case for the Fluke, I can show the case. So I would reduce the risk of the damage. And actually the weather, when I was taking the references back, was horrible. It was raining whole week, and then that day kind of stopped, but it was still cloudy and humid outside. So this is the case I bought for the 732B. It's around 250 USD, not a cheap case. So it's a Pelican 1535 Air. It's actually quite large. You can see you have the wheels, have the handle. Nice rugged case, and then so I put the standard in the ESD protection bag, because all this foam, it's quite ESD aesthetic. And then the standard goes in the center. And actually this case, this size is perfect even for like meter, like Keithley 2002 for example. It can fit here nicely. I can show you with another one. Let me get this around. So I have some random Keithley on the floor. I believe this is pico ammeter, Keithley 6485. So I can use it for illustration, that it fits quite nice. And the thickness is about perfect size for such a half rack 19-inch unit. Another point that I like about Keithley 2002 is that they are small, so you can take them into the backpack or like a case like this and just travel with them in a hand carry luggage, like calibration measurement lab on the move. So that's about the transit case. I'll need to get a much bigger case for 5720, because sometime eventually I'll have to take it with me, and I want to have minimum damage possible for this guy after all that countless days and weeks of work I put into it. Alright, I think that's it for now, and it's about 6:30 p.m. here in Taiwan, Sunday. And tomorrow I have to go to work and earn some more money so I can buy some more equipment. So another small point I wanted to make is, if you guys think this is helpful and want to see more often videos and stuff like that, then I would be happy to accept donations through PayPal. You can just go to the xdevs.com site and click on the PayPal button and donate whatever sum you think is suitable. That will help to pay for calibrations and some more equipment purchases and repairs, which I'm doing all the time. And always open for discussion, so if you have any questions even after the stream, feel free to join xdev/chat or send the email to me, and I'll check and reply everyone involved. Alright, I think that's it. Thanks everyone. And yes, I can share the link. That would be well, you can just go to my site, and that's it. Link is in there. And actually also I'm very happy if you have documentation about test equipment or electronics related stuff, and if you're willing to contribute to our docxdevs.com repository, where I try to mirror every documentation bit I have, then feel free to upload. You can go to docxdevs.com/contact, and there are step procedures how to upload to the FTP server. So that's it. All right. Thanks all. Bye.